you stay up there. Does anybody have questions they want to ask about what she did or how she did it? Okay? All right. How about on this one? Anybody have any questions about this? I find it interesting that they took two different approaches, kind of the same approach, but they started on the left here and went 3 times 4 plus the 2, and over here started on the right. Does it matter? No. But if the number's very many digits, where do you probably want to start? On the right, because it's always the ones place, right? Or to the zeros place.
I was just going to ask if we could do an example in base 12, just because that's the one that I have the most trouble with.
Base 12? Mm-hmm. Sure. How about 3E4T? Go ahead and try that one.
Is it 10?
E is the digit that stands for 11.
Oh.
T is the digit that stands for 10.
Okay, that makes sense.
Got it?
No, could you explain it to me? I was still trying to work out.
E is the single digit that stands for our number 11, and T is the single digit that stands for our number 10. And that would always be given to you in the directions that you're given. Somebody's ready? Come on up. She wants to know if it's right. How many got that? Well, we got quite a few hands. That's a good sign. Okay, let's look at our process. This is what I meant by starting. You get numbers that are a little bit bigger. You probably want to start on the right, because this T is a what? 10 in the ones place, or 12 to the zeros place, right? So she went 10 times the ones place, plus 4 times the 12 to the first place, plus E, which is 11 times 12 to the second. That's 144. Plus a 3 in the what place? 12 to the third. If I would have started here, I'd have to come over here and say, well, that's the 0, the 1, the 2. I'd have to count it over anyway. So it just makes sense to me to start on the right. You can start on the left. Reverse this. Everybody okay? All right. Let's give you this one. base x. What is its value?
I'm moving it to base 10.
We don't know quite how to do this part, but you should know how to do this part. When you've got it, come up and put your answer. Yeah, go ahead and erase the one there. What do you think? And what have we got here? What is this? Does anybody know? Not a quadratic. It's a cubic polynomial. So we just showed you that a number to the base x creates a polynomial. If you want to do a quadratic, you would only have 3 place values, right? Instead of 4. Does that make sense? So this is just like saying 3x cubed plus 4x squared plus x plus 2. Polynomial. That's right? Okay. All right. Let's return to perfect squares. Can somebody tell me about the factors of perfect squares? Refresh our memory. What?
They have 3 factors.
3 factors?
Some have fair and odd.
You have an odd number of factors. Some of them have 3. Why?
Because a perfect square is a number times itself.
Because a number times
The
itself,
factors of a perfect square
And-
would be 2 identical numbers.
and therefore one of the pairs is that number in itself when we don't write the factor twice. So it only appears to have an odd number. That one's being used as its own pair, right? Everybody remember that? Okay. That's important for us just a little bit later on today. What I'd like to ask you is let's use you give this fraction here to a student, and the student says, and you ask them, is this number irrational or is it rational? And he grabs the calculator, and go ahead and grab yours, convert it to a decimal. He converts it to a decimal. What did you get?
0.84.
Point what?
0.843.
0.844. Keep going.
37.
3. Bar over the 3, or
7.
then what? 7, and it just okay. And he says this is an irrational number because the decimal does not terminate and it doesn't repeat in a pattern. What do you say to them? Yep. You agree with them? You're shaking your head. You don't agree?
No, because all rational numbers can be put into a fraction. So the decimal must repeat, which is probably really long and doesn't show on the calculator.
How far out do we have to go?
At least 83 places.
82. It should start to repeat by the time we've got 82. That 83rd one should be a repeat. How do we know that? How do we know that has to happen?
I was just gonna ask why we know that it could be 82.
Yeah. You're absolutely right. This is rational because the definition of a rational number is anything that can be written as a fraction, right? And then we learned that any fraction can be written as a decimal that either terminates or repeats in a pattern. And we look at the denominator and say this one cannot be factored into just 2's or 5's or combinations of 2's or 5's, therefore it will repeat. And yet, you look at your calculator, there's no evidence whatsoever that it repeats. So how do we know that it does? How could we verify that it does? Did you look at this +1 thing that we were talking about? When I convert this to a decimal by hand, how do I do it? Which one's divided by which? If I make my little division house, which one goes in the house? The 7, and the 83 goes out here. The divisor is always the denominator, right? Then 83 is not going to go into 7, so I'll put my decimal right. Annex is 0, and then I'll start going. Well, notice, when I take this in here, it goes 0 times, right? So I've annexed another 0 and asked how many times does 83 go into there? Well, it's going to be 8, since you've given me the answer up here, right? And then I take 8 times 83, right? Get 4. And then I subtract, correct? How many different remainders can I get here? Let's subtract here. We get 6. That which means, so we were over here, that'd be 3, right? Wait a minute. Yep. And then, wait. Because we had to come over 6. That became a 9. There we go. 36, right? How many different remainders can I get? I can get 82 different remainders. Plus 0, but we know it's not going to terminate, so 0 is not going to be one of them. But when I'm dividing by 83, the only remainders I can get are 1 through 82. So by the time I have done this, I'll bring another 0 down and keep going. By the time I do that, there's one remainder, 36. I could get 82 different remainders, but by the time I get to 83, I've got to start repeating again. Does that make sense? Did you look at it with number 7? Yes? Was that part of your homework? We better do it. Let's do 5/7. 5 won't go into there, so 7 goes into there 7 times, right? 49, remainder of 1. Okay? Bring the 0 down, 7 goes into there once. Remainder of 3. Bring that 0 down, goes into there 4 times. 28, remainder of 2. So I had a remainder of 1, a remainder of 3, now I've got a remainder of 2. 7 goes into 20 twice. 14, remainder of 6. 7 goes into 60. How many? 8 times with a remainder of 4. So I've got a remainder of 2, a remainder of 6, a remainder of 4. Bring my 7 goes into 40. How many? 5 times 35. Remainder of 5. Now, 7 goes into 50. And all of a sudden we get this big case of deja vu. I've been here before because 7 into 50, right? And so what's going to go up here? A 7. And then what? A 1. And then a 4, right? And I've exhausted all of the remainders when I'm dividing by 7. The only remainders I can get are 0 through 6. That's 7 different remainders. But 0 we're not going to get because otherwise it would have terminated, right? If you get a remainder of 0, it terminates. So I got 1, 2, 3, 4, 5, 6. And as soon as I get all of them, it's got to start repeating. So if we're to do this, I might get, I have a 36, but I could get all the numbers 1 through 82, but then it'd have to start repeating again. Does that make sense? Because that's the only thing we've got. All right, question.
So, does it have to go through all 82? Or can
No. That is the maximum. It could start to repeat before it exhausts all of them. Yes, that's possible. Here's a case in point. You've all got this one memorized, right? According to that, it should start to repeat after 3 minus 1, 2. But we all know it's 0.3. It only has 1 decimal place. So it could start to repeat before it gets to the denominator minus 1, but it will definitely start to repeat by that time.
Yeah.
So the maximum number of digits in the repetend is always 1 less than the number in the denominator, if it's a repeating decimal. Does that make sense? Okay. Well, let's talk about this then. So if I ask you rational or irrational on this, what do you say? Rational. Why? Not because I can see the repeating pattern in the decimal, because it runs off my... You got to have a big calculator before you find the digits. Put that in Wolfram Alpha and see how many actual digits there are before it starts to repeat. We know because it can be written as a fraction. What if I say this? Square root of 2. Rational or irrational? Go ahead, punch it into your calculator. Take a look. What does it give you? Point what? 1. Oh, let's see. 1.4. 1. 4. So, is it rational or irrational? You're saying irrational. Did you check clear out there and it never did? I mean, did you go clear to infinity and it never started to repeat? Is that how you know? That's how we would have. That's how far we'd have to check, right? And you can't check clear out to infinity. Why do you have to go clear to infinity? Because maybe if you went a little bit further, it'd start to repeat, right? Well, if it starts to repeat, what do we know? It's rational. Because a repeating decimal can be turned into a fraction. So can I turn this into a fraction? Why not?
Because it's not rational.
How do you know it's not?
Because it doesn't turn.
Did you check clear out to infinity?
Not recently.
Nor can we, right?
Right.
But the question I'm trying to ask to get you to think about is, if we looked as far as we could on our calculator here and didn't see it repeating, and we look here, how can we say whether it is or isn't? Well, this one we can say it is because it can be written as a fraction. Can this one be written as a fraction? How do we know?
I thought that if you take the square root of anything that's not a square number, it's automatically irrational.
Why is it?
Because you can't find like a number, like two numbers to multiply together to make that number without going on to infinity. Like that's just like the square root of 2, there's no fraction you can take times another fraction to make 2. Like it just doesn't work. So because the number just keeps going on and on and on. Does that make
What
sense?
about this? There's no whole number that works there, but this is a rational number. What is it? 2/3. Right?
Yeah, that's true.
Okay. The reason I'm asking this question is because we're going to show you how to prove that this is irrational. Okay? And the way is not by looking at the number of, or looking at your digits and see if they repeat after a while, because you can't go out far enough to check, right? Are you ready? We start off by supposing that this is rational. We call this a proof by contradiction. We're going to start out by supposing that the opposite of the thing that we're trying to prove, the opposite of it is true. So we're going to suppose that it's rational. And then what we're going to do is we're going to reason until we encounter a contradiction. If we find a contradiction, then that means that what we supposed must be false. And if this is false, then it must be irrational, right? Let's try that. This is kind of like what the lawyer does. Suppose my client did murder this person. That would mean that he would have to have been at the scene of the crime at the time that it took place, right? And then he would go on to show, but I have witnesses, and we'll call them to the stand in just a moment, to show you that at the time on that date, my client was somewhere else, right? There's a contradiction to the suppose my client is guilty. So therefore he must be innocent. Does everybody see what we're trying to do? We're supposing this is rational, then we're going to find a contradiction to that, and therefore it must be irrational. If it's rational, then I can write it as some fraction a over b, right? Do you agree with me on that? If it is rational? Okay. I can write it as some fraction in lowest terms a over b, and therefore, okay, let me see if you can see what algebra I'm doing. Anybody know what I did to this equation to turn it into that one? Squared both sides. Is that legal?
Yes.
So we haven't done anything wrong yet. All right, now I'm going to do this. If that's true, I submit this is true. Do you agree with me?
Yes.
What did I do?
Times the b squared.
Multiplied both sides by a b squared, right? Okay. Now, if this is a squared, then it's a perfect square, right? Do you agree with me? Some number times itself gives me a perfect square. Therefore, this number right here has an odd number of factors. Do you agree with me on that? Because it's a perfect square. It has to have an odd number of factors. Right? Now, I'm going to cover the 2 up for a minute. B squared is also a perfect square. Therefore, B squared would have a odd number of factors. Correct? So if I were to prime factor this right here, okay, or write down all the factors, a list of all the factors, it would have an odd number. This would have an odd number as well, correct? But if I take those factors and put 2 in as a factor, let's suppose that B has some factors that are 2's. What would you know about those 2's? Let's just take 36. Does it have any 2's in it? 6 times 6, right? And 2 times 3 and 2 times 3. So 2 squared times 3 squared. Since 6 is 2 times 3, 6 squared would be 2 squared times 3 squared. Every single prime factor in a perfect square has what? An even number on its exponent. Has to. Why? This has to be even, this has to be even. If there's another one, it'd have to be even. How come?
Because if you take the square root, then you get even.
Because if you get the square root, it breaks it into equal amounts in each one, right? Does everybody see what she's... Here's another way to look at it. If I added 1 to both of these, right, I get 3 times 3 is 9. 9 is a odd number, right? The only way to get odd numbers when you're multiplying these plus 1 exponents is to have what? All of them be odd. The only way I can get an odd is multiply an odd times an odd. I can't ever multiply by an even or it'll be an even, right? So if I'm going to add 1 to them, that makes them odd. Therefore, they have to be, the original has to be even. You with me? Well, this has got an even number of, because it's a perfect square, it's got an even number on all of its primes. And this one has an even number on all of its primes. But over here, there's an extra 2. So let's suppose that this had some 2's in it. What we would know that it'd have to be 2 to some even power, right? And this would have to be 2 to some even power. But now I've got an extra 2 out here, which means now I've got a odd number of 2's, right? Is equal to something that has an even number of 2's. Is that possible? There's our contradiction. Let's say there aren't any 2's. Let's say it's our perfect square is 3 squared times 5 squared. That's 15 squared, or 225. It still doesn't matter. There's 2 factors of 3 in here and 2 factors of 5 in here, but there aren't any 2's. But notice, every power of 2 has to be, every square number has to be made up of power even powers. And this one would have even powers equal even powers, but then we've got this 2 out here. and they're no longer equal. Does that make sense? I'm not sure I'm getting through. Who's following me that could put it in different words that maybe it would make sense? Nobody's following me? Oh, I'm in real trouble. Have I convinced you that every perfect square has even powers on all of its prime factors? Okay. So if this has got even numbers on all of its prime factors, and this has got even number on all of its prime factors, this number here can't be equal to this number, because the 2 out here times this with even. If there are 2's, it would be even, and this 2 out here would make it odd. If there aren't 2's, then all these are even, but this has a 2, and this one then doesn't have a 2, or at least an odd number of 2.
So what if it was a 4 instead of a 2, which is 2 squared?
Where?
On the B side. Would that make it even, or would it also have to have a 4 on the A side as well?
Yeah, if I had a 4 out here, that's 2 squared, which is even. Therefore, it could be equal to something that's, yeah. You can't have something that has an even number on all of its prime factors and something that has an even with a odd be equal to each other. There's the contradiction, which means our supposition is false, therefore it has to be irrational.
So no matter what is underneath there, unless it's a perfect square, that would kind of throw a monkey wrench in the situation,
Yep.
meaning that
Yep.
it's off kilter, so it's...
So there's a contradiction, therefore it is irrational.
So it could be a 2, or 3, a 5, a 7, or something like
Any
that,
non-perfect square. Yep.
So if the number, like 2 to the power of whatever, if that's even, then it can be
If this was even out here, then I haven't contradicted it. It could be true.
If it's odd, then you're complexing it and it's irrational.
And something with an odd number of 2's can't be equal to something that has an even number of 2's. Because they have to have the same power on them. Okay?
Can we do that, set it equal to A over B? Yeah.
Square root of non-perfect squares.